Let us continue to do that. So we were looking at partially ordered sets. Well, basically we started with sets. Now started with sets. Well, what kind of sets? The sets were usually collections of objects where each object in the collection was of a similar nature. So it could be power set of a set or set of, so this is combinatorial, but it could be non-combinatorial. For example, set of complex numbers. So all the numbers are complex. Just see complex numbers. It could be set of natural numbers and so many other things. Okay. And basically this was a set, but we wanted to solve some problem related to that set, right? For example, here there were problems of, sequence of natural numbers. A long enough sequence will have a long enough monotonic subsequence and things of that nature we had. So basically we wanted to solve problems about those sets. Okay, so we basically decorated the set, right? So basically we started with these sets, and given the problem that we wanted to solve, we decorated the set with a relation, a suitable relation. Decorated the set with a suitable. This was the general strategy we used to solve the problems. Obviously, then we also studied this decoration, that is this relation we put, or the partial order we make out of the set. We studied general properties of these things also, but it started with solving some problems. Decorated the set with a suitable order. Or basically, to put it in more layman kind of terms, is we tried to introduce a sensible notion of comparing the objects of the set. Okay, comparing natural numbers in a different way than the usual comparison, or comparing complex numbers in some way. Okay, now there are many ways to compare the complex numbers, but we have to choose a suitable way, right? Similarly, a power set of a set, how to compare based on subset relation or something, or different things, right? And then we saw that depending on the question, this art of finding the right kind of order was the key to really solve the questions. Then we applied some general theory of these partial orders, said that if any set is partial order, then there are some constraints, right? So the third step was rather mostly to apply some general but easily believable. So the theorems were not non-obvious. The proofs might not be simple, but the theorems were not. But the theorems were very obvious, right? Means the truth was evident. But yeah, so apply some. So now that we could talk about these sets in terms of in terms of order, in terms of comparison, which is such a primitive notion, simple notion. So we're talking about something complicated using something simple, and in that way we are discovering something about the complicated thing. Okay, apply some general results of partial order sets, which were easily evident after you drew some diagrams of. So we also in the process, introduced in parallel the theory of partial ordered set. So in the theory of partial ordered sets of now, so I'll now just use posets. We simultaneously also did develop some theory which we needed, kind of. So we had this. The main thing, I guess, was checking, right? Checking that the notion of relation you introduce is actually an order, which is that the relation that you introduce. So so you are introducing a way to compare things which are not, I mean, on which maybe there is no God-given order, but you're introducing a notion of comparison. You're basically introducing a binary relation, right? But that must satisfy at least some properties, right? So the relation introduced must be an order relation. That is, it must have the transitivity. So all this we have already done. This is just a review. Transitivity, reflexivity, and antisymmetry. Okay. And the second thing we learned was representation of post sets. Obviously, there is much more theory in this, but we don't need it right now, so we will not go into it. Representation, or I should rather say diagrammatic representation of post sets. Right? We had this, and from here we infer and infer some theorems. Obviously, here we looked at the two important things, chains and anti-chains. Okay, because when you introduce an order in these sets, then the problem becomes in terms of chains and anti-chains. Okay, so we had these chains and anti-chains, and then we infer some obvious theorems, and then we apply them here in these problems. Okay, so now there are two directions here. Either one can go and solve more problems and discover more theory, or learn more theory for its own sake. Today, my plan is to not do many problems. We already did some, but rather consolidate the theory more, or rather get more comfortable with this notion and tie up some loose ends in a sense that prove the theorem that we have stated. At least I think one of them we should prove at least. So let's get into that. Okay. Yeah. So the first, so far are there any questions? Because also I had asked to some checks and such to be done last time and last time and so on. So if anyone has tried and has any questions, you can address them first. Okay, so then let's move on. So I'll just start with, I think examples are a good way. So we saw examples of different flavors, right? Let's just see an example of a very different flavor. Okay, so yet another example of partial orders. And the partial order sets are important both obviously in discrete maths, and this is basically a structure that you can introduce on any, that you can give on a collection. Now that collection could be a topology collection of open sets. It could be collection of not trees. I don't know, trees have an order, but collection of certain kinds of graphs, or basically there are many things. Right now, what we will see is collection of matchings, and we'll try to give a partial order on that. So yet another partial order on a collection. So the collection is a little complicated. So let me take my time and define it, and then we will study that collection more in detail later, surely. But yeah, here's the collection. So the collection. So first of all, what we have is the context. We have n men and let's say n women. Okay, or maybe we can just take 10. Or let's just take 5. Okay, let's say 5 men and 5 women. Okay, so we have, what we have is m1, m2. Now I'm just putting these things because it will be needed. So this is the men, and let's say this is the women. So what I'll be doing will be an incomplete example, but it will be incomplete from the perspective of the actual problem that this is about. But it will be good enough for us to discuss this. So I'll just do the incomplete example, but maybe you will not see why it's incomplete. Okay, and then there's nothing theoretically wrong in that. Okay, so the point is that there are 5 men and 5 women. Yeah, and then each man. So basically, we are interested in a matching. We're interested in matching these men with the women. Obviously, so we are so let maybe yeah. So I'll just say that we are interested in matching the men with the men. That's all. Okay. So if I do not give any conditions, then how many matchings are possible? Now, obviously, by matching, I mean that to each man, we want to assign exactly one woman. And for each woman, obviously, then it implies we want to uh, uh, match exactly one man. Okay. So that's all it is to begin with. If there's nothing, if there are no other conditions, then how many matchings are possible? Sorry, can you be louder? Can you be louder? Yes, simple, right? So if there are no conditions, then there are 5 factorial. Okay. But even if we just stick with this 5 factorial, okay, actually there's something called stable matchings that we are interested in. But for now, let's consider there are no condition and the 5 factorial matchings. Already this is a big set. And therefore, we would want to understand it. We would want to set up a hierarchy in this set of matchings, or put some richness, decorate the set of matchings. Huge set already, but 5, it's 5 factorial. That's why we want to decorate and so on. Anyways, let's move forward. So now yes. Yeah. So basically, when you have a set, so let's say this is a set of natural numbers. Okay. If you just start with a natural number, set of natural numbers. So right now, as a set, it is just elements. Okay. Now we would, when I say we want to decorate, I mean, so by the way I'm using, so this is probably just, I'm using it like this. So decorate, I mean here is that put a relation, put a binary relation on the set. Okay. What is one example of binary relation on this set? Is the usual less than relation, right? One, so you relate 1 with 2. This means, this just means 1 is less than 2, 1 is less than 3, 1 is less than 4, and so on. 2 is less than 3, 2 is less than 4. This introduce a relation. Obviously, this is like almost a God-given relation, meaning that before the natural numbers are invented with this relation already, right? It's like it runs in parallel. So, but this decoration, this relation on the natural numbers really makes it an interesting thing to study. Right, we get interesting things like maybe n factorial is bigger than n by 3 to the power n, or some things like that, right? Some interesting things we get with this relation. So that's like, and that helps you to put some more meaning to the set and so on, right? So in the same way, you could decorate n in other ways, right? You could put another binary relation, for example, of division. You will say A is related to B if A divides B. So that's another way to put a decoration on this set. And this would give you new insights. So if you go back to one of the problems we had solved, right? We had used this decoration, this relation, or this partial order to understand the set, because this partial order breaks up the natural numbers in a different way. And that might give you new insights into the thing. So that is the thing. Basically, introduce a partial order. Okay. Yeah. So this, how many? So yeah, this is okay. Now I will in order to make this more interesting, we'll have to put preference list. So each man, and this will lead to a very interesting algorithm called the Gale-Shapley algorithm. Okay, I will discuss that later. But right now it is just okay. Before that, we will discuss something. So right now it is just each man has a preference list. Now, obviously, each woman also has in the usual setup, but for us, it's enough to just know what is going on. Okay, each man has a preference list. Okay, so let's say that the preference list, let's just actually give a preference list M1. M1, let's say, has a preference list like, so you can understand when I write it. It means that W3 is the first in the preference list, and there is a W1, and you can put anything. I mean, just. And similarly, M2 has a preference list. Let's say his preference list is like this, 3, and so on. You see, each man has a preference list. Okay, so I have given you 5 men, 5 women, and the set, the collection that we're interested in is this collection of all matchings. Okay, and now the task for you people is introduce a partial order on the collection of all matchings. Okay, but I'll just say it like this: introduce a notion of comparison, or just decorate this set. Introduce a notion of comparison on the collection. And this is the partial order that we introduce, that you will end up introducing, is the beginning of the theory of matchings in computer science. Otherwise, the theory cannot be, you cannot do much without introducing an order. Okay, it is used to generate all stable matchings. It is used to prove that to generate all stable matchings where there could be 5 factorial of them also. You know, it only takes a linear amount of space to do it because anti-chain length is not too big. And there's just many things. Without this order, without the order that we are going to introduce, it's impossible to study the theory. Okay. So anyways, so that's why this is, so introduce a notion of comparison on the collection of, but for us, just all matchings, no stable, unstable. We have not even defined it, all matchings. So this is a very simple problem. So let's think, okay? We just want to, and actually in some sense, we have already done this problem in a different way, but I'll say it after we want to compare. So set of all matchings, let's call this set, this right here, M. And so there in this, there is matching 1, matching 2, matching 3. I don't know, many matchings. Obviously 120 matchings are there. Keep this preference list in mind. So there, using this preference list in mind, there is some natural order that you can put. Like how is some matching better or bigger than the other? Okay, something like that. Yeah, so you are informally correct, but I'm not writing it because you have to say something more. I mean, otherwise it's not even defined, but you are correct. You are there, I think. So the problem is to see, the point is that there is no one partial order. There is no unique way to decorate a set, right? There are obviously, how many partial orders are there? That's another interesting question. But my point is that there are many partial orders that you can think of. Okay. But which one of them are natural, which one of them are useful, that only time will tell and context will tell, right? What we are trying to do. But yeah, but try to think of some natural order that, like Raghav has already said one. Informally, so one has to complete it otherwise. Okay, no, but women, so I mean, the way I've defined it, the women don't have any preference. Yeah. Okay, so I think let's do one thing. I think since both of you are giving some ideas, let me actually let's actually take 2 matchings and then you guys decide which one of them is bigger. Okay, so that then you can state what you are trying to say. So let's just take this. So let's just take matchings. I'll just randomly draw 2 matchings so that you can point out which one of them is bigger according to your definitions. So there are plenty of matchings. So let's say one of them is okay, but the point is that Yeah, I need to complete. Yes, right. I should complete the preference list. Yeah, so let's quickly write the preference list because that will help us to say things. I mean, you can still describe. So my point is that you can describe the partial order without the preference list, right? You can describe a general scheme, general policy with which you'll do. But still, if we take an example here, then I must give a complete list here. So this is like the opposite. He's the opposite, and and then there are two more. Just some permutation we can take. Four and maybe 3, 1. Or let me do one thing just to make it slightly more interesting. Yes, okay. Yeah. So with respect to this, now let me just draw a matching. So one matching I just draw like this. And let's draw another one. So we want to compare these two. Just simple. Now let's try to compare them. And remember, if you, what you're going to introduce is as you're saying, it may be a partial order. So it may not be possible to compare any two things. The two things might also be incomparable. Okay. Obviously, you may also introduce a total order and so on. We'll prove that any partial order can be extended to a total order using an algorithm. We'll do it soon. Topological sort, some of you may have heard it. Sorry, we ignore the. Okay, so that's certainly sensible. So I'll write it. So maybe just like this. Ignore men matched with same women. Okay. Yeah, okay. In both, I should say that. Okay. Yeah. So A is the set of A is those. So let me just write it in words. Those men who have, I'll just say, higher women in MI than MJ. Is that what? Okay. Okay. So for example, can you say, let's for all of us, let's see what A is for this example. So why don't we have M1? M1 is there, right? So M1 is there. M2? M2 is there? No. No, no, no. M2 is not there. So yeah, so my question to everyone, does everybody understand what A is? So A is the places where MI is winning, where the first matching is winning than the second matching. Those are the men in the first matching which are winning than who have a better time in the first matching than. Yeah, so it will not necessarily be leading. It will not necessarily be leading, but those men which have better choice in the first matching compared to the second. No, no, comparatively, relatively better. They may not get the best. In fact, it's not possible to in this. Yeah. Okay. So then we have M2 out. So M2 is also there. Okay. No, M3 is not there. You're getting confused with your own definition. Yeah. M3 is not there because M3 is worse off in the first one because W3 is down compared W4 is so M3 likes W4 better, right? And but W he's matched with W3 in the first. So yeah, maybe this should be AI is a better word, but yeah, it's okay. And M5. Yes, and yeah, M5. Okay, then what? So B will just be the complement of A always. No, not complement, but maybe apart from the ones you're ignoring. Right, right. That's right. But then what? That will not work. That will not work again. You can see it will not work. That order will not work. So the reason why it will not work is because it is too simple. Matching is a very rich thing. You cannot capture it with some simple cardinality thing. That was a mistake made earlier by other people. I mean, while trying, not a mistake in the sense that yeah, it didn't work in other suggestions earlier in other problems also because the objects were more complicated. And you can just see here, right? Here, cardinality of A is equal to cardinality of B, but these matchings are not same. But the problem again is that then if you're going to say sum of the weights or product of the weights, something like that, then again you see that will not form because two different preference lists might again end up giving the same weight. Yeah, but then that can be amended by giving some weights like powers, 2 to the power something and something, but that will get really complicated and it will not. Sorry, prime, no, prime number. Okay, if you're taking products then prime numbers, but again the problem will be the same. Yeah, that will not work. Yes, but so then what you will do, you'll take the product and then you. No, but then the product. Okay. Oh, no, but you see, okay, no, so yeah, that might work. But then what will you do after that? So you will say weight. So you will define weight of a matching. Weight of a man. Yeah, weight of a man will be the prime number. And then weight of a matching will be the product. And then you will compare the product, and but the product will not be equal. No. But the product can still be. No, product will always be equal, right? It will be all the 5 women, so all the 5 primes will get multiplied. To what? Oh, okay. So you will say, that am I, no, but that is that might work actually. So mi is bigger than or equal to mj if weight of A is bigger than or equal to weight of B. Yes, and product of the weights of the of the things they are matched with, right? And because the matchings are different, yeah, right. Hmm. Okay, so you are saying that to this, to the first in his preference list, no, this may not work. You see, I can give you counter example. So if you give this, so if you give the last preference thing, if you give it 2, and second this preference you give 3, right? So you're going to give it, so you're going to give the prime number to the rank, not to the women, right? But to the rank of the woman in the, yes, right. You prime number to the man, but the correspondingly to which is matched, and one of these prime numbers, right? Yeah, 7 and 11. And so weight of A will be m1 and m2. So m1 is matched with w1, and w1 is 7, so weight will be 7. And then m2 is matched with w2, and for m2 w2 is again second, so it's again 7. Is that right? Like this. That's the weight of A. But you see, the problem is that you're giving the weights to the positions actually, right? But then A and B, the positions may end up being the same. May end up being a permutation. The men are different, right? But the women, so for example, it might be that for M1, it's this gets second in M1's preference. M1 gets the second woman in his preference list, and let's say he gets second. But it's possible that M3 and M4 also get second in MJ, right? M3 gets the second woman in his preference list in MJ. B is for MJ, and he also might get second, and that is not a problem. So this can be equal again. No, but you see, it can still be equal. There is a problem. Oh, so you're giving here. Okay. Let me see. Okay, so what I think Rhythm was asking a question. Yeah. Yes. The problem is that then you see the problem is that I mean you do not want to call MI and MJ equal, right? Different because MI and so no MI can be greater. So if this is a fundamental of partial order, or just logically basically, if you have two distinct elements, then if A and B are distinct, if A and B are in the poset, right, then either A should be bigger than B, A should be less than B, or A is not comparable with B. But you cannot make them equal if they are not equal to begin with. That's because then it's not a partial order. Then it will become a partial order on something else, on some quotient and so on. But yeah, anyways, that doesn't. Okay, so then there is some other. Yes, yes. But there is no preferences for women, so we don't need that. No, that's not important. This question can be answered because women. Yes, yes, because that's, yeah, that can be answered. So the other idea that is being given is give men the this thing. I don't know. You can think about that. That I do not know how it will be sensible matching. Sorry, a sensible notion of ordering. It doesn't sound very sensible to me. Okay. Right. Okay, so let's do that. So then if we give 11 and so we are giving the weight to the man. Okay. So we'll call this 11. Right. No, that makes sense because that's more rich than so 13, 11, 7, 5. Okay, I should start with 3. Anyways, it's a matter. We have these 3. Then if okay, so then if this is what you do, then you will say this if right. So yeah, so the idea is this. The idea is that you take two matchings and you see the places in which mi is winning, that is A. Then you look at the places where mj is winning, and that is B. Okay. Now you see which man is winning in which one. Okay. So if the places where mi is winning, sorry, the places where the places where, yeah, the places where the matching mi is winning, that is the elements of A, right? You look at the elements of A, what is their status, and you multiply their status, and then you take B and you multiply the status, and then you compare it. Okay, so we say this, and this will actually become, maybe it will become a total order, in fact. But then this is not very useful because we do not want to distinguish between men. I mean, that's usually not the context in which this is studied, but I don't know, might be useful somewhere else in some other version of this. So if weight of A is bigger than equal to weight of B, and this weight is nothing but the product. So M1, M2 will be 11 into 7. No, M1, M2. Where is M1? 11 into 13. And this will be 7 into 5. And obviously 11 into 13 is bigger than 7 into 5. So, yeah. Yeah, so then you have to check. So just check if this is, so this is for homework. Check this. It's not hard to check. Check that this is an order relation. So check the 3 properties. Check reflexivity. I mean, it's obviously reflexive, right? Because if the matchings are equal, then the weight will actually be 0 because A and B will be empty, right? If the matchings are actually equal, then there is no difference. So A and B will be empty. So reflexive is clear. Antisymmetry, you have to check. Yeah, it is not difficult. Yes, antisymmetry is not difficult to check. Please do it. Please do it. Unless you do it this, and you will not understand whether you have really understood this or not. Okay, antisymmetry, and also check transitivity. So let me just think if that holds. I mean, I can just say check. So I do not. I don't need to know ahead, but if yes, obviously it will hold. Obviously it will hold, right? Yeah, so you can just check it. Okay, but putting prime numbers and taking products is the key, because two obviously numbers with different primes, product cannot be equal. There is a beauty, right? That's really the beauty of these things. Okay, so do these exercises to understand this order. Okay. But this is not a very useful order in the sense that, I mean, in the sense that you're not using the preference list. It is preferences are more or less, well, I'll not say useless, but we want to use the preference list itself. We don't want to use the weights to give a, okay, to give a. So please note down this question, or you can see this later, but still you can note it down. Let me tell you the order that I'm thinking of. And it is really just a it's not a lexico, it's a kind of a lexicographic order which we had put on the complex numbers. One of the orders we had put on the complex numbers, not yeah, one we put two of, I think we put more than two. No, this will be there, I think. 1 minute. So this is there. Let me remove this. So yeah, so basically I am saying that if you look at this, if you look at these two matchings, so let's, the task. So we're just learning, and so understand that putting the right kind of order is the main thing. Once you do that, then is if you use the right theorem and so on. But coming up with the right order that you want to put, okay. But and you see, if you don't, so if the problem is given like this and you do not want to distinguish between the men, right? If you do not want to distinguish between the men, then it doesn't make sense to use the weights on the men like we just did. Obviously, but that's legally, that's still a legal order. If an order is asked for, if you give that example, it's perfectly correct. Obviously, first we said cardinality, but then cardinality doesn't work, but then you further make it rich. But we do not want to distinguish between the men, and we still want to give an order. Okay, only using the preference list, right? So here is another way in which you can see this matching. So let's call it, this is M1, or let me, you can include the, no, but then you see, whenever you have A, you will have to put the order on the men also, right? If you're going by that method, right? If there are an odd number of men, that's okay. A and B should not be equal, right? Unless they are empty. What may work? Oh, cardinality. No, I do not think. No. Cardinality itself will not work. Try it out, but I do not think that will work. Okay. Cardinality, just taking cardinality will not work. Cardinality is too simple to compare. So basically, problem will be that you will have two different matchings where the cardinality will be same. Like that's, you can make that example, make such examples. Just by symmetry, you can balance it. No. So the point is that if you can view, so you can view M like this as a list. W1, W2, W3. This is the matching. It's not any man, it's a matching. I'm basically just putting the women in a place to which they're matched. And here I will say, since M1 is matched with W2, W1, W4, who is matched with M4, W3, and then you have W5, right? Right. So you see, if you have these two lists, what is the obvious way to compare them? right? You see, so we want to do coordinate wise comparison. Okay, so the idea is to do coordinate wise comparison. Every coordinate in this should be bigger than every coordinate in this, something like that. Okay, coordinate wise comparison. Okay, just like you may introduce, if you have pairs of numbers, you may introduce this order. You may say this if and only if A is bigger than C and B is bigger than. You can put this order, right? This can be a very useful order if you really want to be very strict and get order which is, which is like this, which where it's completely, it should be better. So the first is like for first, this is like completely better than this. Okay, this kind of order is a very strict kind of an order, and it may be needed sometimes. That's the kind, and this will obviously just be a partial order. You cannot compare everything. Here also we will do something similar. You see, coordinate wise comparison means what? So we will say that m is bigger than equal to n if and only if w1 is bigger than w2 in what? Obviously in the preference list of m1. So for m1, w1 must be higher than w2. And this, and w2 must be higher than w1 for whom? Obviously for m2, because that coordinate, second coordinate is for m2. And you understand, right? Third coordinate is for m3. And so w3 must be higher, and like this you go on, right? So basically m must be better than n for all men. That's simply how I can say, right? M should be better or at least as good as n for each man. Like no man is ready to compromise and such, because there is no hierarchy among the men themselves. Okay, so that's the basis of this. And you can again exercise. Yeah. Sorry. Then the two matchings are incomparable. Right? So this is not a total order, but it's a partial order. It's just a partial order, right? Not comparing everything, right? But we want to be very strict. We want to be very strict and say that every man should be better. Otherwise, it's partial order. Now for homework, check that this is a partial order. Yeah, you are right in some sense. A meaningful total order may not be possible. No, it is possible. I mean, you can, right. You are right. In some sense, a meaningful total order, that's a very interesting point actually, right? A meaningful total order will need some sort of a preference. So we will have to give a hierarchy among the men also. Okay. And that is not a very strange idea that, okay, it's not a very strange idea, because think about how we compared complex numbers, right? We said that, or even if you look at your dictionary order, that's exactly what it is, right? You say 2 plus, we give the most preference to the first letter, right, of the word, and then the second letter, and so on. So what did we say? So we had like this. What did we say? We said, okay, we will give the preference, or you can do it in polar form, but the point is that you want to give the preference. We'll say that we give the preference to the real part. So if the real part is bigger, then we say that the number is bigger. So if 3 is bigger than 2, then we say that this is bigger, right? And we forget about the imaginary part. Only if the real parts are equal, then we go to the imaginary parts. If both the words start with the letter 2, then we go to the imaginary part and we compare. And then we go like that. This is actually what is called lexicographic order. This order is incredibly important in many, many places, especially in the theory of polynomials, Grobner basis, and all kinds of things. But it's not useful for complex numbers. That's the next thing I wanted to do, a little non-combinatorial thing. Okay. So this is the thing, and you can check that this is a partial order. Please check this. Okay. So this is just example. Yes. Yeah. It is just relative. It is just relative. The exact number is not important. As long as what M1 gets in M is better than what M1 gets in N, then we say, right? Then it's fine. Then but then if you go to the second coordinate and it has to happen. So for example, these two matchings are incomparable. By our order, these two are incomparable because some men are happier in M and some men are happier in N. So by what Raghav was saying, if you go by his definition, then what must happen is that A must be basically B must be empty. It is the same as saying B is empty. Like no man should be happier in N. That is what B was collecting, right? If you go back to that, the B must be empty is I can state this, and in his construction it would be that B must be empty for M to be dominating. Actually, the word dominate is what is used. This is called a domination order. Okay. No. So see, they get their first choice may not be possible. See, there. So actually, there is no in this preference list. In this preference, it is not possible. So there is no such thing as happy or not happy. It's relative. So what do you want? Right. That's, you agree, right? It's relatively. Yeah. Right. Okay. Yeah. Try. Uh-huh. I am. Yes. So if that happens, like just like in this one, right? So in this example, M1 and M2 are happier in M, and M3 so already yeah. So in this case we say that these are incomparable matchings. No, but no, this is like none of the conditions are just, this is simply that none of the conditions of domination are matched. So this does not hold, and this also does not hold. It is just that. Yes, it is possible. Yeah. Or if you mean to ask something else, then that maybe I'm not understanding. That is right. Yeah. Yeah. So so this is basically, usually when we look at order, we see everything is related to each other, right? But in partial orders, some things may be related, some things may not be related. And actually, some things not being related is what is the usefulness of partial orders, right? I mean, if you have this 120 things, then you just put them on a line, and everything, one of them is bigger, and so on. Everything is comparable. And you just put them on a line, then what do you now learn about it? Nothing, right? More or less. But if you're introducing a way to compare them so that some things are incomparable, some things are comparable, then you get a rich picture. Then you're basically breaking up the collection of matchings into some levels and so on, right? Where things on the same level are incomparable and so on. Then you're basically partitioning the thing into an interesting way, and then you can learn things about it, right? So this was just an example. Yeah, let us now, this just took a little more time because we're doing this for this matching thing for the first time, but we will soon see more of this, and then we don't have to, then it will be faster. But I also wanted to give an example in just extend this in complex, this one of the problems we were doing last time in complex numbers, because yeah, let's do that. So there is no, this is what I want to show. There is no useful order on C. Now this is something that some of us were saying. I think they are not here today, this class, but saying that this seems to be the case, that there is no useful order. Otherwise, you would be seeing it being used, right? Complex numbers. Obviously, this word useful has to be defined. This is not to say that there is no order on the complex numbers, okay? Every set has a partial order. Every set has at least one. There is a total order. We had seen that the last time. I just, okay. Yes, that way, right? Or you can just say real part. But yeah, basically, there's a total order also. Every set has at least one partial order. This is obviously silly because you can just give no order, and that's also partial. That is extremely partial, but you cannot deny that it's, yeah. But yeah, every set has at least one partial order. There is really no problem with that. Okay. In fact, every set has at least one total order. There is no problem with this either. I mean, just let's list the, at least for the sets that you have looked at so far, just list them out in your own way you feel like, right? Just list them as you feel like. And so that will be a total order. There is no problem with this either. I mean, that is why when we give an order, we want the order to be meaningful. Because orders you can give anyway, right? But it has to be to the context. It has to gel well with the context. Okay, that's why giving an order, arbitrary order, is not a problem. Or an order is just a relation, some small relation. You can make many relations, right? It's not a problem, because that has to just do with the set and its cardinality. It has to do nothing with the meaning of the set. Right. In fact, there is a big result. This is a very deep result. Every set has at least, this is a very deep result. This we cannot prove. It takes a lot of time to, yeah. But this is a very important result. But it's not important in Olympiad maths and discrete maths too much. That's why I'll not say about this at all. But I just mention it. Every set has at least one well order. A well order is extremely, it's not the it is not the well ordered. I mean, it is. I don't. Well, what do I mean to say? Oh, yeah, yeah. So you may know what a well order is, right? We say that. I mean, that's the same as induction, right? Just saying roughly, n natural numbers, n is well ordered, right? Well, what does it mean? Well, it just means that every, what does it mean? Well, there are many ways to say it, but 1 minute. Yeah, it just means every set has a minimum. Every subset has, this is what well ordered means, right? Every subset has a minimum. And this is what makes induction work, if you just think a little bit. Okay, but that's what basically, if you don't just forget about induction, maybe you have not seen the connection, but point is that the natural numbers is well ordered. Okay, and again, automatic theory and so on, this natural numbers and functions from n to n, computable functions, so on, understanding well ordered induction and so on is the first thing. But the natural numbers is well ordered. We all know this, that every subset has minimum, obviously, because yeah, not all sets are well ordered. The integers are not well ordered. Yeah, you can take just, you can just do the integers. Yeah, and so on. So integers are not well ordered and so on. But reals are not well ordered, right? R is not well ordered, obviously. Right? You can just take 0, 1. There is no minimum. Right? I mean, the 0 is there, but 0 is not a minimum. 0 is not in the set. Minimum has to be in the set. That is important. Okay. R is not well ordered, and so on. But there is some other order you can put on R, and this is a magical result. There is some other order you can put on R such that it becomes well ordered. Okay, so on every set you can put some strange order, and we will never show you what that order is. We will just prove that there exists, and it's not possible to construct it. Okay, that's the nature of it. Okay, so every set has at least one well order, and this is called the well ordering principle. And this is what makes the higher mathematics would just stop if this was not there. All the theorems in higher mathematics is using this. And you can think, right? I mean, the mathematics that we do will not work if there was no induction. You cannot prove anything if there is no, if induction is not there. You cannot even prove associativity of natural numbers if induction is not there, right? Induction is an axiom that has to be put to make so that you can prove things about natural numbers. In the same way, if you want to prove things about sets which are bigger than natural numbers and which are not well ordered, unless you can put a well ordering, you cannot do it. So it's a bit like that. Okay, and this is equivalent in some other forms is there which are more obvious, but I will not say them. But this is a very, it's incredibly deep theorem. So if you take a course in logic, this will probably be, or maybe not proved there. If you take a course in set theory, maybe it. Anyway, this is interesting result. No, but what I wanted to say is that there is no useful order on C. So first of all, let me just quickly review total order on C. So total order review means all of us know is total order on C. Obviously, we just said, I just said in a different way, slightly just CD. I'll just say that this is bigger if A is, maybe just put it like this. If A is bigger than C, or if A is equal to C, if A is bigger than C, you basically, the real part is more valuable. Okay. Or, but you can see this is obviously a nonsense order, right? It will not be very good because of this nature. Or if A is equal to C, then we compare B and D. This is obviously a total order, right? You can compare any two things in this way. This is the way numbers are compared. You can think about, right? We basically look at the digits, and the highest digit to compare, and we just need to look at that, right? When you're comparing to big numbers, what you're looking at first? You're looking at the highest digits first, right? You're not looking at the lowest digits. So it's just like that. This is just obvious. So there is a total order, but then the question is, why is this not very useful? Yes, right. That's the point. I mean, in the complex plane, real imaginary, there's no such thing, right? So it's not. So yeah, intuitively, it feels like it is not a good one. Okay, but to say it mathematically that it is not a good order. Okay, but this is not good because so the reason is that when you put an order on a set, see the complex numbers are not just a set. The complex numbers come with an addition and they come with a multiplication. That's right. Yeah, they come with an addition and they come with a multiplication. So if you are putting an order, okay, it's not a good, okay, this is not good because I'll explain this. It does not, basically it doesn't merge well with the two operations that we have. This can be said more abstractly, but since we have not seen binary operations abstractly, so I'm not saying it. But because it does not mix well with these two operations, okay? Because to say it formally, it does not, again, these operations and such are what we're looking at. Semi-groups, we'll see later, we'll study them a little bit. Again, they are something that's important in both computer science and mathematics. Computer science, they're useful in automata theory because every finite set automata corresponds to a semi-group and blah, blah, blah. So we'll see. So because it does not respect addition and multiplication. Let us see. I've not checked this. Let us see if it respects addition. Does it respect addition? So what do I mean by respect addition? Yeah, it is just the most obvious thing you can think of, in a sense that what we want the following. We want that if Z1 is bigger than Z2, then, or rather if and only if, Z1 plus Z3 should be bigger than Z2 plus Z3. So you want this, isn't it? All of us agree, right? I mean, if you're putting an order on the complex number, this must happen. Otherwise, it just will not be useful, right? Otherwise, just putting an order on pairs of numbers, not on complex numbers. Okay? So is this satisfied? Can we check that? Let us think about that. Does this work? Yes, yes, I think so, right? We just take some examples. Sorry, 1 minute, I got a little lost. Yes, just take examples. Yeah, I think this will work here. Okay, let's take examples. If you take 1 plus 2i, and let's just take a little, example. 1 plus 2i is bigger than 5i, right? Because this is 0. 0 plus 5i. So this is your Z1 and this is Z2. Now, if you're going to add a Z3, so yeah, it will respect addition. If you just add a Z3, sorry, this is not good. If you add a Z3, right? I mean, the Z3 will make equal contribution to the real and imaginary parts, right? If you break it down. So I'm not exactly taking an example, but if you put some numbers and see, you will see it's holding. But at the same time, you can also just, or maybe after doing something, you can see this, right? Now, obviously, 1 plus a is going to be bigger than a, obviously, right? So it will remain bigger. So yes, this is true. It does hold. Does everybody see that? Right? So if you have Z1 and Z2, and let's say that the real part of Z1 is bigger than the real part of Z2, then when you add some real number, when you add some complex number, obviously the real part is going to get shifted equally. So it will remain bigger in the first number. is Z1 plus Z3. So the answer to this is yes. So yeah, addition is saved because I mean the pairs of numbers also have addition, but what they don't have is multiplication. So this holds. Please just take a minute and check. I'll just wait. Yeah. Now let us think about, now multiplication is more delicate. That is really where complex numbers are. That's where complex numbers are different. Complex numbers, we basically have a sort of a multiplication. We introduce a multiplication operation is what makes the complex numbers, right? And also the division, which is, so which is different actually. Okay, means not everything that has a multiplication has a division, like integers don't have a division. So what we also want is if z1 is bigger than z2, then well, this is has to be quantified, qualified a little bit, not quantified, in the sense that if you multiply, so what am I doing? Yeah, if z1 is bigger than z2, then if you multiply by z3, then it must remain bigger for all z3 greater than 0. So do you agree with this? This, I mean, this is something again which you want, right? If something is a positive number or rather greater than 0, which makes sense here. Oh my God, what is happening here? Oh yes, yeah, z2, yeah, right? Yeah. So this is another thing which we desire, right? I mean, if you're going to give an order to something, this has multiplication and this, better this hold. Now let us investigate, does this hold? Let's take example again, okay? Okay, so first of all, let's think of a complex number which is positive. Well, there are many examples, but I will take I, because I is what is the game changer. That is really the new thing, right? And it can be used to describe the entire complex numbers. So I, we know, is positive. Right? I is positive. Yeah. Now think, does this hold? So A plus IB bigger than C plus ID, does that imply, question mark, that this is this very strange property of I, or this is the property of I. Why not? Yes. Obviously, Z2 is on. Yes. So that's the thing. And then Z2 is 0. Yeah, I think that gives a counterexample, right? So then I times I becomes -1, but -1 is not bigger than 0. Even with respect to this order that we have, -1 is not bigger than 0, right? So that's contradiction. So I is positive, but then I is not positive. So what is I? Where is I? So I is neither positive nor negative, and that's the problem. Something you can understand. Just this is already there. Even if I don't say anything more, this is what it is. This is a proof. Okay. So you see, we had an order, but then it was not an order. It's an order, but it's not a useful order. Now, what you need to now do is basically do this argument in general, right? You need to not assume any rule and still show that there is no total order. So you basically start with any total order. Okay, there is no useful total order. So there is no total order on the complex numbers satisfying properties A and B. There is no useful total order, on C satisfying. We have not proved this. Okay, A and B. So this is not an important exercise for all of us, but just try it. I had done this in the complex numbers class long time back, in the first class of it, but just do this. I mean, basically I've already done it, basically. I mean, we didn't use this much. If you just go back and look at the proof, I'll just do it again. Okay, so there is no total order. That is the magic. So you basically prove, you'll end up proving that you cannot put any order on C, which is satisfying these two. This is called field axioms. Anyways, that's not important. It becomes an order. So C is not an ordered field. Okay, and that makes C very difficult to deal with in a lot of places. But all that will not be said in this class. That will be said in the complex class. Okay, so I think that's it for today. Next time I will prove the theorems. We'll prove the theorems, and we'll also do some problems. I think we'll start with problems next time. We'll do 2 problems, then we'll prove the theorems that we have stated earlier and we'll be using again in the other problems. Okay, so that's it for today.